Well, welcome back to SanfordFlipMath. This is Pre-Calculus. We are deep in the throes of section 1.5. We are in the Demana Waits Foley Kennedy book for Pre-Calculus. Again, this is section 1.5. And we are talking about transformations of functions and their graphs. And in other words, specifically for us, we want to look at how the values of a graph, or how the values of a function, how the graph of a function changes as we make changes to the equation. Okay. Well, there are a lot of kind of theoremish kind of things in section 5 of the book. Again, this comes from the Demana Waits Foley Kennedy Pre-Calculus book. I don't want to be accused of plagiarizing or anything. This is full credit to them for doing all of this, and this is by Addison Wesley Longman. I think the publishing company has probably changed now, but so anyway, that's the idea. So one of the things I want to kind of boil these rules down to some basic ideas so that it doesn't feel so symbolic. I think this feels very abstract as it is now. So we're going to start out with just looking at a couple of graphs, looking at what happens, tie it into what's going on with this, with the things that we see on this from the book. Okay? All right, so here we go. I want to start with just y equals x squared, and so this is a parent function. This is what your book calls a basic function, and there's the graph. I just get a real good feel for what it looks like. We're talking about a parabola. It has, you know, like it, the x value 1 has a y value of 1. Negative 1 squared is also 1. 2 squared is 4. Negative 2 squared also 4. So I mean, and this 0 squared is 0. So this is pretty typical. I mean, we've seen this, you know, lots of times. So I mean, there's nothing real shocking about that. What I want to do though is look at, okay, so that's all well and good. What if though we have y equals x minus 2 squared? Okay, so looks like so what I did was I made a change. Okay, so again, this is x minus 2 squared. So it should make sense that something to do with something to the 2 happened as a result of 2. So I want, you know, as we look back at the graph, I want to look again at what significance is that 2. Okay. Well, hard to see on here. Let me push trace. I'm going to switch functions, and let's do a little bit of tracing. And it looks like the vertex. Now, I'm not on a nice decimal, clean decimal screen. In fact, I'll go ahead and do that just so it's a little more obvious. Look at where the vertex is. Okay, so the vertex used to be at 0, 0. If I switch functions by pushing the up arrow, now the vertex has moved to the right. Okay, so just a quick note that when I did x minus 2 inside the equation, it moved to the right. Okay, I want to pop back to this. Okay, so when the parent function was y equals x squared, and then we went to y equals x minus 2 squared, what happened was it moved 2 units to the right. Okay, so what I need you to see is that's this situation, isn't it? Now, what we did was a translation of all of the xy's became x plus 2y. Now, what this notation means is this is a translation, which means slide or shift or move. And we went, the x values actually became 2 more than what they were. Okay, so this is called mapping notation. And what it does is it illustrates, oh, not mapping notations, just mapping notation. And it basically says exactly what happens to the ordered pairs. Okay, so when it moved 2 to the right, the x values became x plus 2. 2 more than what they were. The y values didn't change. Okay. Now I want to do a little contrast with, okay, I want to delete that parenthesis. I want x squared minus 2. Okay, and we'll do a little comparison. Okay, so here's x squared again, and here's x squared minus 2. Okay, so just for the record, it went down 2. Went down 2 when we are comparing it's x squared minus 2, as opposed to the original was just y equals x squared. Okay, let's go back over here again. Okay, so y equals x squared minus 2. It shifted down 2. Okay, so again, let's take a peek at the notation. So it again was a translation, a slide, a shift. The x's didn't change this time. The y's became 2 less. Okay. So notice this was the y equals f of x. This was the original function, and then there was something subtracted over here. And there it is. Okay. Now, what I'd like to do is make a generalization about this. Okay. So here we go, and then I'll come back to the stretches and shrinks and flips and all that kind of stuff afterwards. Okay. If you have something added or subtracted, and we'll do more examples in a second, it's going to be a slide, shift, translation, etc. It moves the graph. Okay, and so that's one part. If there's addition or subtraction, it moves the graph. Doesn't stretch it, doesn't shrink it, doesn't make it bigger, doesn't make it smaller, it just moves it. Okay? If that addition or subtraction is inside the function, like for instance, inside the squaring, where'd that equation go? It was farther up. If it was inside the squaring, notice this said minus, and what we really did was plus, or toward the positives. If it's inside, it affects things horizontally. It's about x. Okay, it's with regard to x. And lastly, it is inverse to what you would think. So when it's addition, it's really subtraction towards the negatives. When it's subtraction, it's really addition toward the positives. Okay. Conversely, or inversely, if it's outside, it's vertical. It's about up or down. It's about y. And you do what it says. Don't do the inverse. Do what it says. Okay? This is a big deal. This is like the heart of everything. Okay? And just again, to tie it in, notice this was minus 2 on the outside of the squaring. Here's the x squared, but this minus 2 is on the outside. And we actually shifted vertically, and it said minus, so we went towards the minuses. We went down 2. Okay, keep that in mind. Okay, so that summarizes what's going on, and so we've talked about that in terms of the addition and the subtraction, but understand that those overall conjectures, those overall ideas translate directly to pretty much any multiplication, division, addition, subtraction, positive, negative, fractions, whole numbers version of any of this. Okay, so as we look at this rule, if I'm dividing inside, so inside means it's about x. So it's horizontal. Inside is also inverse. So that means that if I divide by something inside this function, the effect would be to multiply in the x direction. So if I'm dividing inside that function by, let's say, 3, I'm going to, on the graph, multiply by 3. Okay, and we'll talk about some mapping notation that'll work for that as well. Okay. Similarly, if I multiply on the outside, you do what it says, and it's vertical. Okay, so this is vertical. Okay, so anything on the outside is going to be vertical, and anything on the inside is going to be horizontal. Okay, I really think we just need to kind of look at some examples. Okay, so let's say we're looking at y equals absolute value of x. Okay, and we saw some we see some of this on the worksheet. I know this year we did some in class with this ahead of time already. And if I do just a little graph of this, okay, something like that, and it's absolute value. So this side looks like that, and we're looking at a V shape. Okay. All right. So I want to do some multiplying here. So if I do 3 times the absolute value of x, the effect on the graph then, okay, is, again, this is outside, so it deals with y, it's vertical, and we do what it says. Okay, so in other words, because this is a stretch or a shrink, this is going to be an S, not a T. Okay, and S is actually for scale change. Okay, in some cases you might call it a dilation. So, and all of the x, y's will be mapped on, well, the x's don't change, but the y's are multiplied by 3. So notice this point 1, 1 becomes the point 1, 3. This point 2, 2 becomes the point 2, 6. This point 2, 3 becomes the point, 3, 3 becomes the point 3, 9. 0, 0 is 0, 0, because when you multiply the y value by 3, it's still there. Okay, and etc. Okay, so again, just to see what just happened, okay, I'm going to pick that point 2, 2. It gets mapped onto 2, 3 times 2. That y value goes in there, which is 2, 6. And that's this point and this point. It was vertically stretched. Okay? Okay, let's pop here, and I'm just going to clone that, and let's go right here. All right, I want to go back to, let's do y equals x squared as the parent function. Okay, and I'm just doing some quick points on this, 1 squared and 2 squared, negative 1 squared, negative 2 squared. Okay, so this is the parent function. We're going to do a scale change. And let's do 3x, y. Okay, so what this means is I'm going to multiply the x's by 3. Now, I'm actually going to do this, so I'm starting with the notation this time. This is the mapping notation. This notation says exactly what happens. And in just a minute, we'll build the equation that'll make this happen. Okay? So this says we're going to multiply the x's by 3. In other words, it's a horizontal stretch of 3. So this x value at this point 1, 1, it becomes 3, 1. 0, 0 becomes 0, 0. I'm multiplying the x's by 3. Multiplying this x by 3. This x gets multiplied by 3, so now it's negative 6. Okay, so now the question is, what's the equation? Okay, now remember, if it's horizontal, in other words about x, it had to come from the inside, and it has to be inverse. So the equation has to be, well, it's something squared. Well, the inverse of multiplying by 3 would be dividing by 3. Okay, so this is x over 3 squared. Okay, let's just take a look at that on the graph. So I have x squared. Okay, let me go back to y equals x squared. Okay, and then let's go down here. Now let's clear that out. And this was x divided by 3 squared. Okay, so let's look at the graph. So here's y equals x squared, and there's x over 3 squared. Okay, so take a look at that, compare it to that, look pretty good. Okay, so if I take just a quick look at the table, if I look at this x value of 1, I get 0.1, I'm sorry, I get 1, not that. And then if I look at the x value that's 3 times that, I really didn't want to do that, sorry. Here it is right here, it was already on there. So 3 times that now has that y value. If I look at negative 1, the y value was 1. If I look at 3 times negative 1, so all I'm trying to establish is that the point that used to have the y value of 1 now has an x value triple that. Okay? All right, so let's just do, let's see, let me see where we're at with time, if I can find it. There it is, 17, oh, we're good. All right. All right, next up, let's do y equals 2 times x plus 1 squared minus 3. Okay. Now, when we're trying to graph this, now, and the way this is going to go is I'm going to ask you for a parent function. I'm going to ask for what transformations. And I need you to be able to say it in words, and in the mapping notation. Okay, now, so there are really a couple of things that are going on here. Well, really 3 if you count them all. Oh, sorry. We're going to graph both the parent and the final graph. Okay. All right. So first thing we're going to do is identify the parent function. And really what you're doing is you're identifying the function that has the same basic shape and characteristics. This is the function that your book calls a basic function. Now, as soon as I look at this equation, I'm seeing this squared, and I'm thinking to myself, parabola, quadratic, those are the things that immediately key in for me. So automatically, I'm thinking parent function y equals x squared. It's not absolute value of x, it's not square root of x, it's not x cubed, it's not sine of x, it's not log of x, it's x squared. So immediately, I'm thinking that the parent function has a graph that looks something like this, okay? And this is kind of the standard parabola, and usually we go one to the left, 1 to the right, 2 to the left, 2 to the right, and then we do a little sketch. And because of the squaring, it's right 1, up 1, and then if you go back to the vertex, it's right 2, up 4, so it's 2 squared, okay? All right, so here's the parent function. Now, I need you to think in terms of order of operations. Okay. As we look at this function, notice there's a lovely 2 there. Not sure what happened there, but that's fine. Okay. That 2 is connected by multiplication. Okay. Anything that deals with multiplication or division is a scale change. So it's, in other words, it's going to be a stretch or a shrink. Okay. And in terms of order of operations, multiplication and division come before addition and subtraction. So I need to deal with multiplication or division first before I deal with addition and subtraction. Okay, so when I do this, this 2 is on the outside. So that means it's going to be vertical, in other words, about y. It's going to have to do with the y values. Okay. Since it's multiplication, also because it's out in the outside, do what it says. It's not the inverse. Do what it says. Okay. So this says times 2. So that means this part of it is a scale change, or a stretch or shrink, that affects the y values by multiplying them by 2. This is what happens first. Okay, so this is in symbols. In words, this is a vertical stretch of factor 2. Okay, so that's what's going on because of the 2 times. Okay. Now, I have 2 things in terms of addition and subtraction going on. The x plus 1 is inside, so that means it's horizontal, which means it's about x. And addition subtraction, remember, is a slide, a move, a translation. Okay, translation, move, shift, all synonyms there. Okay. Okay, so one other thing, when it's inside, it's inverse. It's just the way it is. It doesn't feel right, but graph it, you'll see. So that means that as we do a translation, the xy's will be taken, instead of x plus 1, they're actually moved left 1. I'll do the y's in just a second. Okay, so we have a shift, move, translation, left 1. Okay, now popping back to the equation again, there's a minus 3 on the end. It's not inside the squaring. So inside and outside have to do with this squaring. Well, so x plus 1 is inside being squared. This minus 3 is on the outside of that squaring. Excuse me. Okay, so that minus 3 is outside. That means it's about y. It's vertical. Sorry, I didn't follow the same order. And do what it says. So that means that I'm going to, it says minus 3, so I'm going to do y minus 3. So it's shifted left 1 and down 3. Don't say down negative 3, because by saying down negative, it ends up really being up. So either say, if you're talking about wording, you could say it shifted vertically negative 3. I think most people are going to be more comfortable saying it shifted down 3. Okay? All right, so that's the translation. Now, one other little bit of notation to go with this, and I know you're thinking, dang, that's already enough. Okay? There is such a transformation as called a linear transformation. Don't mix up transformation and translation. Transformation just means change. Translation is the slide or shift. A linear transformation is any combo, any combination of scale change and translation. Well, this was a combination of scale change and translation. Okay, so the notation, L for linear, and the reason it's called linear is because it's like y equals mx plus b. Well, the m is the multiplication, and the b is the addition or subtraction. So here we go. In the x direction, all that happened was the x minus 1. Okay, so this is going to be mapped onto x minus 1. In the y direction, we had times 2, and then minus 3 in that order. Multiplication first, then the subtraction. So this is a linear transformation. This is basically just saying we're going to do two things, okay? Well, that's a lot. I need to wrap this up. Just, again, a quick reiteration, and I know you can rewind and stuff, but I just want to kind of, again, go back and say, okay, if it's inside, it's horizontal, it's about x, and it's inverse. So it's addition, then it moved left. If it's multiplication, then it's really divided, if etc. Okay? If it's on the outside, then it's vertical. It's about y. Do what it says. Follow order of operation. Okay, so again, all that means is multiplication, division first, then addition and subtraction. Okay. All right, well, I'm sure we'll be talking about this more in class, and thanks for hanging with me. Sorry it went a little long. It's a lot of stuff to jam in there, and we'll be doing more examples in class. See you tomorrow.